compounds are a bit more complicated. In compounds, particularly ionic compounds, the surface tension can be strongly anisotropic. A classic example is sodium chloride. If you take the 1,0,0 plane, the face plane in sodium chloride, and you start counting ions, you will quickly conclude that that 1,0,0 plane is electrically neutral. There are as many positive ions as there are negative ions, so it's electrically neutral. If, on the other hand, you were to try to make a sodium chloride crystal with a 1,1,1 plane, the 1,1,1 plane, the diagonal plane, has only one kind of ion in it. So you would create a surface which had a preponderance of one charge, and it would have a much higher energy. If you've ever looked closely at a grain of salt, perhaps the most obvious thing you notice about it is it's basically a cube, and that's the reason it wants to have low energy surfaces. In fact, a major function of surface tension is to control the shapes that solids have, the equilibrium or external shape. Metals, one of the reasons we don't think of metals as being crystalline is that you just let them solidify, and usually they solidify in some kind of blobby shape, and it seems to be fairly amorphous. Well, the reason for that is that in a metal, the surface tension is relatively isotropic. So if we ask ourselves, how can we minimize the total surface energy? If the surface tension is the same for every surface, we just want to minimize the surface area per unit volume. And the figure that minimizes surface area per unit volume is a sphere. So if you take water, isotropic surface tension, and you let it drop in a vacuum so that the pushing through the air doesn't change its shape, it will become a sphere. If you take a metal, to a very good first approximation, it will tend to form as a sphere. You pour it on the floor and let it solidify, it tends to solidify as a sphere. This incident, well, I'll get to that later, but you can take this too far. If sigma is anisotropic, then you will want to choose a shape that maximizes low energy surfaces, and you'll tend to get a faceted crystal. Example, rock salt tends to come out looking like a cube. An awful lot of minerals have hexagonal structures, and they will want to be hexagonal prisms. Now, when you go to mineralogy and you start looking at things that we like to call crystals because they have very defined shapes, they don't have the defined shapes because they're thermodynamically any different than a metal. They have those well-defined shapes because, particularly because of their ionicity, when they're ionic, their surface tension is highly anisotropic. So you very much want to produce a shape that minimizes the area of high energy surfaces and maximizes the area of low energy surfaces. And that will be the usual thing. In rock salt, you wind up with a cube. A cube looks something like this. It's bounded by low tension surfaces. And that the anisotropy of the surface tension is such that you can accept a much larger area so long as that area is associated with low energy surfaces. And for that reason that when you see something that you look at immediately and you say, aha, this is a crystal because it's got all these well-defined surfaces on it, this is why. Not that it's more crystalline than a metal, it's more anisotropic. And that's usually because ionicity in the compound makes you have a very, very strong tendency towards surfaces that are electrically neutral. So you can very often just look at the crystal structure predict what the shape of the crystal is going to be. Cubes for rock salt and HCl structures, hexagonal prisms for things that have hexagonal structures, ionic things. The hexagonal prisms produce much more spectacular and pretty crystals than the cubes. Those are the things you see on the side of the road up in this area. Internal interfaces. The most common internal interfaces, particularly in structural materials, are, well, electronic materials as well, are grain boundary and two-phase interfaces. The only, a typical engineering material, most engineering materials are polycrystalline. They consist of a great many small crystals that are stuck together to form the solid. Those crystals are stuck together at boundaries. If the boundary is a boundary between two identical crystals, they're just slightly in different orientation, then this is called a grain boundary, and these are called grains. Many materials contain more than one phase, more than one different material. The boundaries, the grain boundaries, if you want, that are between different materials are called two-phase interfaces. Grain boundaries separate individual crystals of the same material. Two-phase interfaces separate crystals of different materials. Let me give you some examples. This is what generates a microstructure. This is well, this is actually just plain old-fashioned eutectic solder, which has been processed to create equiax grains. In the sense that if you look at here are the individual grains in the material, and they're relatively equiax, they're kind of symmetric figures. The light ones are tin, the dark one's lead. This particular material is a 63-10-37 lead, and the interaction between the tin and lead are such that there's a pretty close division. The tin is almost pure tin, the lead is almost pure lead. So here we have a two-phase mixture. Within the two-phase mixture, you see lots of grain boundaries. Here you see a bunch of tin grains side by side, and here are the boundaries in between the grains. You also have a lot of two-phase boundaries. Here are interfaces. Here's tin, here's lead, and there's the interface between them. Yeah.
What would be the benefit of having larger grain boundaries versus smaller grain boundaries? Is it more valuable?
It depends on what you want to do. The reason that you like this equiax structure in 6337 solder is that this gives you much, much better properties in fatigue. Your contacts will be much more longer. Your circuit will be much more reliable if your solder looks like this. One of the problems we're having right now, kind of off the subject just real quick, is now because of the drive to get rid of lead, we move to solders, electrical solders, that are almost entirely tin. They have a little bit of silver, a little bit of copper, but basically tin. So instead of getting a two-phase structure like this, we have all tin. And with an all tin structure, it's much more difficult with the simple, see solder, you really just solidify the stuff. If you have almost pure tin, it's very, very difficult to get that in a fine-grained microstructure, which for mechanical reasons you'd really like to have. So in fact, there's an international effort at the moment. How can we refine the grain size of lead-free, tin-rich solders in these very, very fine contacts? Yeah.
You have TDM footage on investing on multi grain.
Do I have one?
The transmission electronics.
On what?
That video of the
Mm-hmm.
You have footage on something that has different, I guess, grain boundaries.
Actually, I'll show you something in just a minute. Okay. So this is one kind of microstructure. Another very different microstructure, which is also an eutectic material, like this happens to be tin, bismuth tin, is a much more complex structure that looks like this. In this case, we have two-phase interfaces predominant. There are very few grain boundaries in the interior of these single-phase regions. You can persuade microstructures, and particularly multi-phase microstructures, to look many different ways. And depending on how you make the microstructure look, you can influence and control the properties. Bismuth tin like this actually has rather poor mechanical properties. If I just reprocess the bismuth tin so it looks like this, it becomes the first great what's called superplastic material. You can stretch it like bubble gum, and it will hardly break. Where in this microstructure right here, mechanical behavior is rather poor. So the grain configuration makes a very, very big difference in what the properties are going to be. The low angle, well, the structure of grain boundaries is an important issue. For our purposes, let me just distinguish two types. One is a low angle grain boundary, where we have two crystals, two grains, same material, same crystal structure, that are only slightly misaligned with respect to one another. If this is true, the grain boundary can be just an array of dislocations, edge dislocations, that cause these crystals to match together with a slightly different tip. And in fact, just given the tilt, you can compute what the density of dislocations happens to be. The interesting thing about these low angle boundaries is that they tend to be mobile. In fact, the very first experiment that was ever done that clearly demonstrated the mobility of dislocations under load was done by Earl Parker and Jack Washburn, both of them deceased now, right here in Berkeley back in 1948. What they did was they took a single crystal of zinc and they processed it so that they formed a low angle boundary right here, which is an array of dislocations. Then they showed that if they loaded the crystal, they could make that whole array of dislocations move. And you could see it move because there's a kink in the surface where that boundary is, and that kink would move as they loaded it up one way or another. So that was a low angle boundary. These things tend to be mobile. Now I wonder if I can get this to play. Now we have, of course, much better ways of looking at these things. This is a piece of a polygranular aluminum film that's thin enough that we can see through it. And this is also going to be indented. Here's the grain boundary. I've outlined it. Here's the free surface. What you're going to see, if the movie works right, is that this boundary is very mobile. It's a low angle boundary, and it dances all over the place as we indent it. So let's see if I can get it to play. Yeah, there it goes. All right, here's the indenter coming up now. Oops. Oh shoot, this thing's tied into the, so I can't point while the movie's going on. Boundary is moving to the right. There it is, then it snaps back, then it moves to the right again, then it snaps back, then it moves to the right again. It's flapping like a flag as we deform the material. In the next, I'll hear a bunch of stills that show you that. Here was the initial configuration where the boundary was. After the indentation is done, it ends up back in exactly the same place. But in between, see, here's where it was. You see it's moved all the way over to there. A little later, it's jumped back to here. A little later, it's moved over to there, and it eventually ends up back in the same place. What's happening here? Well, actually, these are low angle boundaries. So, just to give you the theory real quick, since this is a low angle boundary, if these dislocations move, they move the boundary with them. So what tends to happen is I press down on this boundary right here, on the left-hand side, is that the low angle boundary moves. It moves a little bit out, and then it will shed a dislocation. When it sheds a dislocation, it pops back. Then it moves out again, sheds another dislocation, and pops back. So this flagellation, if you want, this flag waving at the boundary, is an understandable process. My point is just that these particular kinds of boundaries can be very mobile. The fact that they separate two grains does not mean they're fixed at all. They can move around quite a bit, particularly when they're low angle. The other kind of boundary is a high angle boundary. And here is a atomic image of a relatively high angle boundary between two aluminum grains. The structure here, you see, gets a little complicated. There are ways to describe the structure, and there are people who specialize in generating models of that sort, which can be very useful and very helpful. They're too complicated for us to worry about in this course. The point is just that here, this is a much higher angle boundary, and it's not possible to really describe this as a simple array of dislocations. It can still be mobile, but it's not as a simple array of dislocations. High angle boundaries, unlike low angle boundaries, are particularly likely sites for chemical segregation. If I have a high angle boundary, then along this boundary, things don't fit very well. There are holes, there are channels, there are things along this boundary. And those poorly fitting sites along the boundary are places where solute atoms can go. One of the problems that we have in the mechanical properties of the materials is that there is a tendency for these boundaries to pick up solute atoms, bad things like sulfur and arsenic and such things, and so they become very brittle. And we will have embrittlement problems that people who make structural materials are constantly having to fight that have to do with the ability of these high angle boundaries to pick up solutes and become poisoned. Coherent boundaries. When we form a second phase particle, we can have precipitation in the solid state just like we have it in the liquid state. In your chemistry laboratories, I'm sure you've been time or another, you mix two liquids and outdrop a whole bunch of solid precipitates. That can also happen in the solid state. And it can be a very important process in controlling the properties of materials, to introduce into the material a controlled distribution of precipitates. But when the precipitate is very small, the ratio between its surface to its volume is huge. So that if this surface would have a high energy, this little thing couldn't form at all inside the solid. So if we look at very small precipitates inside solids, they almost always adopt structures so that they are coherent with the surrounding material. And form is things like this, where for all intents and purposes, all that's happened here is that the red atoms have ordered on the background crystal sites. Here's a well-defined precipitate, here's the boundary of it. Here's an example. This one doesn't fit quite as well. In fact, here are two examples. This is aluminum. One of the effective ways of hardening aluminum alloys by throwing in precipitates is to put in silicon or silicon germanium. The aluminum has a face-centered cubic structure. Silicon, or in this case silicon germanium mixture, is diamond cubic. And it really doesn't fit very well with the aluminum. But it can form a coherent boundary by taking, remember, the diamond cubic lattice has a face-centered cubic framework with half the tetrahedral woods filled. So the silicon germanium can form a coherent interface with the aluminum, and it in fact does that. And you see it right here. This is 2 nanometers, so this is maybe 10 nanometers apart. Very, very tiny particle that formed in the solid state. Well, not only that, while this particle can form a coherent boundary, that's a relatively high energy boundary because silicon and germanium don't fit very well. It turns out that this alloy also contains copper. And there is a phase, aluminum to copper, the so-called theta phase, that also wants to form. The easiest place for the theta phase to form is on silicon germanium sticking out and growing into the aluminum. And here, the theta phase has formed a coherent boundary with the silicon germanium and is trying very hard to maintain a coherent boundary with the surrounding aluminum. That's why, incidentally, this aluminum to copper precipitate forms as this so-called theta phase in the theta structure. That's not the structure aluminum to copper would like to have, but it is a structure that lets it form a coherent interface with aluminum and with silicon germanium. So that's the structure that forms when we allow this phase to come out of an aluminum, silicon, germanium, copper alloy. And it's very effective in hardening the material. Anyway, whenever you form little particles in the solid state, if you're going to form them at all, they pretty much have to be coherent. They have to form coherent interfaces, and that will often cause them to adopt crystal structures that permit those coherent interfaces to form. Stacking faults. I mentioned before that we can have dislocations that are partial dislocations, in which case the Burgers vector from B to B gets split into two, B to C and C back to B again. And where the first partial dislocation, the one that carries the B to C slip, forms, behind it, these atoms which ought to be in B positions are in C positions. That's called a stacking fault. And in aluminum and such things, we will often find our dislocations, copper is even a classic example, split into two partials separated by a stacking fault. How far the splitting will be depends on how much energy this surface defect, the stacking fault, has. In aluminum, the splitting is very narrow, because the stacking fault energy, the energy of putting the atoms in the wrong sequence, in aluminum is very high, and copper is relatively low. So in copper, you see partial dislocations that are widely split with a stacking fault behind them. You also, partial dislocations, this is a picture of, this is a wide split. This is a titanium 46.5 aluminum, basically a TiAl alloy. And here you see these broad surfaces. Here are the dislocations. This is a thin foil, so these surfaces run through the foil. Here are the dislocations widely split. Here's the stacking fault between them. these stacking faults, incidentally, sometimes produce very, very attractive patterns, sort of like who was the famous painter who did the geometric designs. You sometimes get those stacking faults. And Yokomoto, who's one of the very distinguished Japanese steel metallurgists, spent a year with me 25 years ago. And his wife, he was working on iron manganese alloys, which form very interesting stacking fault patterns. And his wife, who was an artist, would take the photographs from the transmission electron microscope, color them, and sell them in art shows in Japan. So, oops, what did I do? There we go. Okay. Yeah, we finish up with twins. I'm just about to write down today, too. Another kind of internal defect is a twin. A twin boundary is a boundary in which the planes of atoms are mirrored about the surface of the boundary. The easiest kind of twin to visualize, you find twins in virtually all kinds of crystals, the easiest kind to visualize is in face-centered cubic materials, where if I have a stacking that looks like this, ABC, ABC, and then it reverses, CBA, CBA. This plane would be a twin plane. The material on this side is twinned or reflected with respect to the material over here. This is actually a deformation mechanism, because if I cause this twin to form, this material, which used to be up here, gets shifted down there. So there's a shear involved. And twinning is a deformation mechanism that you, I don't know if you've ever, probably haven't. If you take a bulk sample of tin, even at room temperature, tin is not that strong. You can probably bend a bar of tin in your bare hands. And if you bend a bar of tin, you will get tin cry. It will protest loudly that you're bending it. What that tin cry comes from, tin is kind of a bizarre crystal structure. And even at room temperature, it tends to form by twinning. It forms these twin planes, and these atoms all shift together. When they all shift together, they release energy. And the energy comes out in the form of noise. So you hear the bar complain as you bend it, and it's called tin cry. So you'll get in other materials. Zinc also tends to do that. So a twin boundary is something like this. A stacking fault is just a change in the stacking sequence, as we just described. You can get stacking faults by dislocations, as I just described. It's also common, particularly in face-centered cubic materials, to get what we call growth faults. Just as the material solidifies, as the ABC stacking is coming in, you'll get an error. What's called an intrinsic fault, in which the A plane here is missing, or an extrinsic fault where an extra plane has been added. And just as the crystal grows, these things will occur with some frequency. And perhaps when you look at copper alloys later on in laboratory, the TA will point out to you some of the growth faults that you see in the microstructure. Okay, I think that's all I got to say about surfaces. It is. So we finished there today, and on Monday we'll talk about volume defects. And if you came a little late, we've already decided that the midterm exam will be on the Wednesday before spring break. I don't have the date here.